Hello, my name is Martin Navarro. I'm in Dr. Yap's class for mathematical modeling. Today I'm going to be explaining some methods for the gap filling method of random forest. Along with that, I'm going to be explaining the bootstrapping method, how random forest works, and a little bit of decision trees because we need that knowledge in order to use a random forest. So we're going to start off with bootstrapping, and the bootstrapping is a method of how you get the data for a decision tree from a big data set. So basically what bootstrapping is you get data from a big data set. So this is our big data set. And you get the data with replacements. So we're going to make this a random data set. So the data set are usually the outcomes. In this particular set, I'm going to have outcomes, just a simple outcome of yeses or nos. So I'm just going to do y's for no's, yeses, and's for no's, and y's for yeses, just randomly throughout there. I'm just honestly writing them as I go, and this is going to be completely random. So say that the way that this works, like I said, so we would get this little data set here, and well, I guess this guy will include inside. So this is one data set here, and this data set would contain 3 yeses and 3 nos. It came out even just because it did. And after you had this subset, you would put that data back in there. So that's where the replacement comes in, and then from there you would just get another data set. And that would be your other subset. So this subset right here is going to have surprising 5 no's and 1 yes. Now you just do the same thing, return that in there, and you just get another random data set. So this is the idea behind bootstrapping. The reason that we do this is because every tree is going to have unique data in it. And what this does, it eliminates variance. It eliminates the bias of choosing the data because it's totally random. And what this presents is variance in the trees. So what variance is the fact that each tree is going to have different data. They're not all going to have the same data. The reason that we use bootstrapping is because say there's an outlier in some other type of data, and probably not in this set, but if you had like another data set and you have an outlier in it, or if the distribution was a normal in it, bootstrapping provides you with better results for your mean, your standard deviation, and also your standard error. So it's something that helps us a lot when you're analyzing data instead of just analyzing the whole data set as a whole. So each of these actually is going to turn into a tree. So I'll just go ahead and explain what a decision tree is. A decision tree, in our case, we actually went, Nick made his own data, and deciding whether or not a student would go into the master's program. So we're going to stick to our simple yeses and nos outcomes. So for this particular tree, we're going to have a random data set, and let's just say there was 5 yeses and 2 nos. So then you determine attributes in here. So one attribute that's really good is the income a person makes. That's going to determine whether or not they want to go to a master's program or not. So if they're between $20,000 and $40,000 a year, that's one. And if they're between $40,000 and $60,000, see how much that influence. So randomly, we're gonna know like there's 2 people that make between $20,000 and $40,000, and those 2 people are gonna say yes, and they're gonna go to college. So this part of the tree actually finishes. In this group, we're gonna have 5 people that make between $40,000 and $60,000. So these are your 5 people, 3 yeses, 2 nos, and since you have that, so that means that 3 of these outcomes 3 of the people that make 40,000 and 60,000 are gonna go to college. 2 of them are gonna not go to college. So I mean, just based off of that, then we'll just look at their employment status. So that's bad. Employed, not employed. And then from there, there'll be 2 people that aren't employed, 2, 3 people that are employed, and from there we'll see the 2 people that are employed. Those people are gonna go to the master's program, and the 3 people that are employed, one will go. He has more aspirations. He wants to make more than 60K, and 2 won't go. So this is pretty much what a basic decision tree is. The reason I do these is because, so from this comes from a randomized bootstrapping data set. So you get a subset of it, and this subset turns into a tree. So you get decision trees based off of that, and you get decisions. So each of these is actually its own tree. So from that is where, so there's a decision tree from each data set. So from there, we actually go ahead and we get a random forest. So what a random forest is actually, it's consisted of many trees. So pretty much what a random forest would do, you'd get all your decision trees. So let's just say it's data subset here, subset here, subset here, another subset here. I mean, I could draw these out, but each one of these is pretty much a tree. So this would be a forest. And in order to get a result from this forest, what we do is we pretty much get the mean. So since there is 5 trees here, then we add up all the results of the trees. So depending on, so all the yeses and nos, we would add them all up. You add all the trees up, and you divide by the amount of trees. It would be 5 divided by 5. But that's the simple way of explaining it. What you're doing is you're dividing all the outcomes of each tree by the amount of trees that there is to get a better outcome, and then depending on that is whether you're going to determine whether you're going to go to college. It's whether it's going to be a yes, whether it's going to be a no. So the reason that we actually use random forests is because they prevent overfitting. So overfitting won't occur in a tree. No overfitting. They're not very sensitive to outliers. So an outlier won't affect the decision of a tree. And this is the reason that you do bootstrapping, to prevent that. So bootstrapping plays an important part in random forest. And it's a very effective way. I mean, this whole thing is based off gap filling. It's a very effective method for estimating missing data. And that's what we really want to do. And the last part that I didn't really talk about and that I want to talk about. So we'll put these side by side. We'll put the forest and we'll put the tree. So here you go. So a tree would be considered a weak learner. The reason that it's considered a weak learner is because it only has a small portion of the data. So this is just a small portion of the data. A forest, in turn, is called a strong learner. And this is because it has more of the data. So look, here's another. It has more of the data, and the way to kind of explain it is the reason it's a strong learner is because it's made up of a bunch of weak learners, and this is the reason that we use a forest, because when you have a bunch of weak learners, it becomes a strong learner and you get a better outcome.